Okay, so today we'll be beginning a new chapter or section of a chapter. But before we get into that, there's something I want to clarify, a little mistake I believe that I made explanation during the last class. Let me just put that up on screen for you guys. Can you see the book?
Mm,
Can you see the
no,
PDF? You can't see the PDF being displayed?
no,
Sobia?
no.
No?
I can't.
Adam?
Well, now I can.
Okay. Okay, so what I want to clarify is the working of the bimetallic strip in a thermostat or an iron, right? And I believe what I said the last time, I haven't gone back and checked the recording, but I said that, the higher up the knob is, the hotter it gets, and that's not how it works. So if you recall the working of the bimetallic strip, right? And so over here you have the copper on top. If I can just, yeah. So you have the copper on top and the iron on the lower side, and so the copper expands more and it's hot, and it will cause the strip to bend downwards in this case. So how the control knob for a thermostat works in this case for an iron is the hotter you want the iron to get, the tighter you would turn the knob, pushing down on the contact. How that would help, right? If it's pushing down on the contact, so it's tightly pressed against the bimetallic strip. And so, right, for that, right, the contact is going to this heater circuit, both of these over here, as you can see. And for that connection to break, the bimetallic strip would have to get quite hot to bend enough out of the way for the circuit to break and stop the heating if you want it to get very hot. If you don't want it to get as hot, you will keep the knob, you know, it'll be away from the contact or just slightly touching the contact. And so when the it gets even a little hot, as soon as the bimetallic strip starts to bend, the contact will break, and so it won't get as hot, right? So if it's pressing against the bimetallic strip hard, and so a lot of heating would be required and a lot of bending and expansion in the bimetallic strip to actually pull away and break the circuit, as opposed to when you want to keep the temperature low, right? So you keep the knob up or less tightly screwed in, and so that would make it easier. Even little heat, even little expansion, even a little bending, just a bit, would enable the, the bimetallic strip to move away and break the connection, right, with the contact and therefore to the heater. So, right, clarification for that. Is that clear how that works?
Yes.
Okay. So, with that clarification done, we can now proceed to talking about specific heat capacity. Let me just get my pen. Right. So first, let's talk about internal energy. Internal energy is the
Sir, if you're writing something, we can see the textbook, not the whiteboard.
Ah, just when I thought I'd shared correctly. Okay, you can see the whiteboard. Yes.
Yeah.
Okay. So internal energy is the average kinetic energy of the particles of a substance. Basically. Right, so we know from the particle theory that the particles of any substance have energy and they are in motion, right? And so the average kinetic energy of the particles of any body or any substance or an object, whatever you want to call it, is called the internal energy. And this is related to temperature. Why? Because when you raise the temperature, right, the particles gain kinetic energy, right? And so the average kinetic energy obviously also goes up. And all of this, when you measure this, when you measure the average kinetic energy of a body, you will get its temperature. Right, so the temperature of a body is a measure of the average kinetic energy of that body.
Excuse me.
Yeah.
Is, kinetic, is kinetic energy and average kinetic energy are different?
What and what are different?
Kinetic energy and average kinetic energy.
Average kinetic energy takes into account all the particles of a body. Over here, we're talking about the kinetic energy of individual particles. So they're not different, right? An average is an average. You take the overall, right? Right. So maybe you've got a value of 10 on one of these, 11 on the other, 9 on the third, 12 on the fourth, and you take all of them and you take an average and you see where you are. Okay. So, right, it's basically coming around full circle, right? Internal energy is a measure of, right, the average kinetic energy, which is basically a measure of temperature. So how hot or cold, as we call it in terms of temperature, an object is basically a measure of its internal energy or the average kinetic energy. So all these three things, right, are pretty much the same. Now, right, talking about thermal energy and temperature. Right, so temperature is the, again, the average kinetic energy. Thermal energy is not the same as temperature. Okay, so the example to give is, you know, a red hot spark versus boiling water. Right, so boiling water we know is at 100 degrees centigrade. A red hot spark, let's say it's of a metal, and so most likely it is, right, the temperature of this guy is much greater than 100 degrees centigrade. So in terms of temperature, the spark is much hotter than the boiling water. Okay, in terms of temperature. But what about thermal energy? Right, a spark is small, right, and so you can't really use it to heat something or to transfer thermal energy to something that is colder. Right, it won't really make that
Like,
much of a difference.
isn't thermal energy itself a heat energy?
Hmm?
Isn't thermal energy itself a heat energy?
Heat energy and thermal energy are the same thing, right? Heat and thermal energy. Uh, right, scientifically, they, to be precise, they call it thermal energy. So why is this realistic, right? In terms of thermal energy, the boiling water has much more thermal energy than the spark. And why is that? Is because the particles of boiling water are far more than the particles of the spark, right? And each particle, even though individually has less energy, right, for the water individually has less energy, but in total has more energy. Does that make sense?
Can you please explain that again?
Okay, look at it this way. You have a 10 rupee note, and your friend has a, right, 500 rupee note. Which one's more?
500.
Obviously. But you got an entire bundle of a 10 rupee note, right? So you got 100 of these. So how much that, how much does that make?
10,000. No, 10,000, I guess.
1,000.
Yeah.
So who has more money?
Me.
Yes, right? So in terms of temperature, the spark has a higher temperature, right? So it's this guy, right? The boiling water particles individually have less energy, but there are lots of them, right? And so in total, they have more energy.
So individually they're not much, but when they're combined, they are more.
Yes, strength in numbers.
Okay. It's like teamwork and solo work.
Uh, well, teamwork doesn't really work the way you think it does. I don't know.
I mean, in situation like that. Giving example, sir.
Yeah, right. In teamwork, it's mostly two guys taking all the work, doing all the work, and the other guy is
And
just standing there for the picture.
yeah.
Okay. So, right, how much energy can you get? You can get more energy from the boiling water than you get from the spark because its temperature is higher than water, undoubtedly. But that's it, right? Or to make the example clearer, let's say that the analogy. Let's change it up a bit. It's 50, right? So 50 is still more than 10, and he has, right, this other guy has 10 of these, and so that brings it up to 500. So it's still coming up to 500. but obviously it's not as much as the 1000.
Yeah.
Okay, clear?
Yeah.
So right now, the thing about thermal energy is that it is always transferred from a body at a higher temperature to one at lower temperature. So, right, something for you to remember. Thermal energy is transferred from a body of higher temperature on a body at a higher temperature to a body at a lower temperature. Okay, so this is something you need to understand and all right.
Yes.
Now, what would happen if that spark that we were talking about fell into the water? Where would the thermal energy flow?
With the water?
Hmm?
Mm. Wouldn't it lose it all its energy?
If the spark
It's
falls
in the water, yeah.
into boiling water, what would happen? Right? How will the thermal energy flow? Will it move from the water to the spark or the spark to the water?
From the spark to the water.
It will move from the spark to the water. Why? Because it moves from higher temperature to lower temperature. So the temperature of the spark is higher. So the thermal energy will be transferred to the water, even though the total thermal energy of water is higher, right? But because the temperature, so the average, when you're taking the average, right, the temperature of water is lower than the temperature of the spark. So thermal energy will flow from the spark to the water. Right now, obviously, if you had like a large chunk of metal, heated metal, then the scenario would be different. Why? Because not only would the temperature of the large chunk of metal be higher if you're obviously heating it, right, near melting, or if you had like a bucket of molten iron or something, right? So if you have like a bucket of molten iron, and so obviously the temperature is going to be higher than water, bucket of boiling water. So I'll just keep that blue. So not only is the temperature going to be higher, but in this case, because there's more of it, you're probably going to have more thermal energy with the bucket of molten iron as well. Why? Because you got more of it. You've got a lot more particles at a lot higher temperature, and so right, more thermal energy to go over. Does that make sense?
Yeah.
Yes.
Okay. Ah. Now, specific heat capacity. Specific heat capacity is the amount, right, of energy, heat energy required, thermal energy, to raise required per unit, let's do this, the amount of heat required per unit mass per unit temperature increase. All right, what does that mean? In simpler words, it is the amount of energy required to raise the temperature of a substance. Right, of a particular mass. By 1 degree centigrade. Okay. And why are they using the term specific? Because when they use the term specific in science and physics, right, that means per unit mass. So mass is being taken into consideration. What does this mean? Right, it means that if I have a mass of 1 kilogram and I want to raise the temperature of that by 1 degree centigrade, how much energy would I need? Right, and so the amount of energy to increase the temperature of and this is to like make it standard, right? Obviously you're going to have different masses, and so different masses would need varying amounts of energy, but you get an idea with this, right? So for example, the specific heat capacity of water is 4,200, right? I'm not giving it the unit right now. It's 4,200, right? You need 4,200 joules of energy to raise the temperature of 1 kilogram of water, right? Which is in this case 1 liter, because it's the same, right? By 1 degree centigrade. So for every 1 degree rise, the temperature is going from 20 to 21 to 22 to 23, and we're talking about 1 kilogram of water. And so for every increase by 1 degree centigrade, you need to input 4,200 joules of energy into that 1 kilogram of water for every 1 degree increase in temperature. Okay. Now, this value is different for different substances. Some substances get hotter faster, while others are slower. The example given in the book is, I believe, water versus paraffin wax. Right, so they compare 1 kilogram of water versus a kilogram of paraffin wax. So it's a type of wax. And right, what the result is that the paraffin wax gets hotter faster for the same amount of energy, right, than the water, right? The temperature rise for the paraffin is about twice as much. So if I'm putting in 1 arrow over here, I'm putting in 2 over here, right? Paraffin wax is getting twice as hot for the same amount of energy being put in as compared to the water. So that would mean, for example, if you're putting in 4,200 joules right? Water is going from 20 to 21, and the wax is going from 20 to 22, for example. Okay, so different substances require different amounts of energy per unit mass, so per kilo, to raise the temperature by 1 degree centigrade. Now there is, right, a formula for this, and calculations are also involved, right? So
Can you please start?
yeah,
Can you please start again? Because समझ नहीं आ रहा.
from where?
The specific heat capacity.
Specific heat capacity is how much heat energy you need to give a mass of a particular substance. Mass, you understand mass, right?
Yeah.
Right. So how much energy you need to supply to a certain mass of a substance to raise the temperature of that substance, that mass of substance, by 1 degree centigrade. Just by 1 degree centigrade. Okay.
Yeah.
That is specific heat capacity. So I gave the example of water whose specific heat capacity, it needs 4,200 joules to raise the temperature of 1 kilogram of water by 1 degree centigrade. So raising the temperature of water from 21 to 22, that's a 1 degree rise in temperature. You will have to supply 4,200 joules of energy.
The change of temperature is taking place in the water. Am I right?
In the example that we're talking about, it depends on which substance you're talking about.
Okay, so whatever substance we're talking, that substance will change its temperature by 1 degree, right?
And the amount of energy required for that change would be different,
Oh, okay.
right? It depends on the substance. Some substances require more energy, some substances require less energy, and the substances that require lesser energy for an increase in temperature will get hotter faster. The other substances that require more energy would get hotter slower, because they need more energy for their temperature to increase by each degree.
Okay.
Aram, does that make sense?
Yeah.
Okay, so the example, right, wax versus water. Wax gets hotter faster. It needs less energy for an increase in its temperature as compared to water. And to standardize this, to make the understanding easier, we talk about 1 kilogram of a substance, how much energy 1 kilogram of a substance needs to have a temperature increase of 1 degree centigrade. Now, if that's clear, right, as I mentioned that there is a formula involved. So for a mass M, that is receiving energy, so that's delta E, which results in a rise in temperature. So that is delta theta. Remember, theta is for degree centigrade, right? So delta theta. And so specific heat capacity which is given with the symbol lowercase c, lowercase c equals to, it is, right, the energy required per unit mass. So energy required per unit mass for a change in per unit temperature increase, right? And so this is your formula that you need to remember for specific heat capacity. C, lowercase c, equals to delta E upon m delta theta, where again the lowercase c is the specific heat capacity of a certain material. It depends. M is the mass of the material. The temperature rise is given by delta theta, right? And the energy involved is given by delta E. And so
Okay.
what are the units? The units, right? In this case, the delta E is energy, so that's joules divided by kilogram degree centigrade, right? For temperature, or right, you can write it as joules per kilogram degree centigrade, right? Yeah, and you want to put this in brackets so that, right, you know that the kilogram and the degrees centigrade are both in the denominator when you're writing it with a slash for the denominator. So specific heat capacity doesn't have something fancy like Newton or Pascal or something, right? It's just the units going over there. All right. Now
Yes.
Yes.
let's do a question.
Oh my God.
Oh, but before that, you can rearrange this thing. Remember rearranging? And so
Yeah. That
if you want to find how much energy is
we make
utilized,
that the subject.
right? And so delta E equals to P M delta theta, right? Which is mass or MC delta theta as they've given in the text. So let's do it that way. MC delta theta. So that's mass multiplied by the specific heat capacity multiplied by the change in temperature. You put all of that together, you will get how much energy was utilized. Okay.
Mhm.
Yes.
So here's a question. It's one of the worked examples, right? If, how many is it? 20,000 joules are supplied to a mass of 5 kilograms. And the temperature rises from 15 to 25 degrees centigrade. What is the specific heat capacity of this mass? And so you've got C equals to delta E upon M delta theta. Plug in the values, you've got 20,000 divided by mass of 5. And how much is the temperature change?
10.
The 10.
Right, so 25 minus 15, right? And so you've got 10. So you've got 20,000 upon 50, and that would give you how much?
40,000.
400.
40,000?
400.
Yeah.
What are you doing?
20, that's 20,000, right?
That's 20,000 divided by 50.
Yeah.
All right, just give me a sec. Sorry. All right, so did you figure that out? How much should we have?
Yeah.
What's your
400.
answer?
The same as Haram. It's 400.
400. The good thing we come down from 40,000.
Yeah.
So it's 400 joules, right, per kilogram degree centigrade. That is the specific heat capacity of whatever substance it is that we are dealing with. Okay.
Okay.
Now, obviously, right. Let's do another question that's going to involve this equation.
Which equation?
This one.
Ah, okay.
So they're asking you for how much energy. Question. They have a mass of 3 kilograms, right, of material of specific heat capacity. So the specific heat capacity is 500 joules per kilogram degree centigrade, right, and the temperature rise is 10 degrees centigrade. So you have delta E. So just to be, what's the energy? And so delta E equals to mc delta theta, which will give you 3 into 500 into 10, which will give you how much?
15,000.
15,000,
Yeah.
right? And what would we put over here? 15,000 what?
You.
Joules, right? How are you getting joules? You've got kilograms over here for the mass. We've got joules divided by kilograms degrees centigrade for the specific capacity, and it's being multiplied by the change in temperature. So, right, we're getting rid of both of these. We're only left with joules for the energy, right? And so the energy you would need to, supply for raising the temperature by 10 degrees of this mass with this heat capacity is 15,000 joules.
Okay.
Okay.
Yes.
Yeah.
Okay. Now, what's, in case of water, right? Water has a particularly high specific heat capacity. And so, how is that important? So, right, the specific heat capacity of water specific heat capacity of water is greater than that of sand or land, right, or soil. Why? Because this guy is 4,200 and this guy is 800, right? So it's about 5 times as more, right?
Yeah.
Specific heat capacity of water is about 5 times or more than 5 times higher than that of soil. And we're saying soil, you can say earth, say whatever, right? So land is basically made of soil or earth. And what that would mean is that water gets hotter far more slowly than land. Okay? So if you take the same mass of water and sand or land or soil, right, you would need, like, there's you could say that the land would be 5 times hotter than the water, right? Or water would need 5 times the energy for the same rise in temperature, right? A change in temperature of 1 degree centigrade. So how does that help? That helps because, right, for example, islands are surrounded by water. And so the climate over there is generally cooler, right, as compared to large land masses that are away from water. For example, Central Asia. So, you take a continent, you take any part that is within that, and so it's going to be hotter. It's not surrounded by water, there's no cooling effect. And when I mention cooling effect, because water has such a high specific heat capacity as compared to other similar substances, water is actually used as a coolant. Right, it's used as a coolant in heating systems. Right, for example, it's used as a coolant in the radiator of cars or other, right, heating systems, because it will take a lot of energy to get that water to get hot. Also, talking about, the difference between land and soil, if you've ever been to the beach during midday and you step on the sand and it's really hot, like you can't stand on the sand, and so you quickly jog across to the water, and when you reach the water, comparative to the land, it feels really cool, right? It's not as hot as the land. There you have, right, practical experience about, right? So why is it important? Well, it helps maintain the cooler temperatures of the earth, right? 70% of the earth is water. It's not land, right? And so absorbing heat from the atmosphere and all of that, and then going into, the environmental aspect of this particular property. So yes, pretty important. Okay.
I can continue.
Hmm?
Nothing.
Okay. So
Matthew said you have 14 minutes left.
yeah. So next up is melting, boiling, and evaporation. So we know that when a solid is heated, right, a change of state occurs, and it turns into a liquid, and the liquid turns into a gas, right? The temperature at which a solid changes into a liquid is called the melting temperature. Right? And the opposite also happens. So a liquid can freeze and turn into a solid. And when it does, right, it's called the freezing temperature. So for a pure substance, one that does not have anything else mixed in, so for example, pure water, right, it's going to have a fixed melting temperature. So for water, it is 0 degrees centigrade. And so when ice, which is the solid form of water, is melting, right, all of it is going to melt at 0 degrees centigrade. And when that is occurring, right, during melting, right, there is no temperature change. Right, unless, or sorry, until all the ice has turned into water. And then the same applies when going from liquid to gas. Right, so that is the boiling temperature. And so when liquid starts, when a pure substance, so when pure water begins to boil and turn into water vapor, which is the gaseous form, and so that happens at 100 degrees centigrade in case of water. And until all the liquid has boiled into gas, right, there will be no temperature change. Right, so the boiling temperature and the melting temperature for a pure substance is fixed, and it stays that way until a complete change of state has not occurred. Right, so this is complete change of state. And it goes for the other way around as well. Right, so the freezing temperature for liquid going to a solid is, right, in case of water, is the same. Right, so it's 0 degrees centigrade in case of water. And so when liquid water begins to freeze at 0 degrees centigrade, the temperature will not change until all of the liquid has turned to solid ice, right, and a complete change of state has occurred. And similarly for condensation, when water vapor is condensing back into liquid, right, it's going to happen at 100 degrees centigrade, right, and until that change of state for that pure substance has not occurred completely, the temperature will not change. Now the question is, right, if both are happening, right, for example, melting and freezing are both happening at the same temperature, then why is it either melting or freezing? Why is it not like somewhere in between? Do you understand my question?
Altitude.
No. This depends, and similarly for boiling and condensation, this depends whether the substance is gaining or losing heat. That's the thing. For example, you take ice out of the freezer from -4 degrees centigrade or whatever it is, and you put it out, and outside right now maybe it's like 22 degrees centigrade, and so it's gaining heat, right? And so when it starts going from -4, -3, -2, -1, 0, right, for whatever mass of ice it is, because it's gaining heat, it's going to melt at 0 degrees centigrade, right? And until all of it is melted, whatever I just explained, But if it's the reverse, you take water that's at 22 degrees centigrade, you put it into the freezer, right? And in that case, it's getting colder, so it's losing energy, it's losing heat. And so that would go for freezing because it's losing. So when it goes from 22 all the way down to 0, it's going to undergo freezing from liquid to solid. And once a complete change of state has occurred, right, all the water, liquid water, is turned to ice, only then will it go further down to the -4 degrees centigrade, that is perhaps the temperature of your freezer. Does that make sense?
Yes.
Right? And similarly for boiling and condensation. Right? Same thing. Whether you're gaining, the substance is gaining or losing heat. Okay. Now, I think I'll stop here. This is an introduction to whatever we're going to talk about. Hopefully, I'll be able to, I'm hoping I'll be able to push this chapter tomorrow, right? And then we'll be done with chapter 2.2. So let's see. But yeah, I'm stopping here for the day and I'll pick this up and continue tomorrow. Any questions?
No.
All good?
Yes.
All right. Then see you next time, inshallah.
Inshallah.
Okay,
Okay.
Allah Hafiz.
Allah.